everybody, this is Angelbert Morales from E. Rodriguez Vocational High School, your science guide for today's episode. Welcome to Ciencia, because science is not only amazing, but fun! Before we start, be sure that you have with you your module in Physics 1. Today's lesson consists of qualitative and quantitative analysis of Newton's first law of motion. Let's start with quantitative analysis. I have here pictures of different objects. Signboard suspended by cables attached to the ceiling. A rock sitting on top of another rock. A set of books sitting on a table. A car on a ramp. What do these objects have in common? You are correct. All of them are in a state of rest. Newton's first law of motion tells us that the net force acting on each of these objects must be zero. That is, the forces acting on each of them must be balanced. When the net external force acting on an object is zero, the object is said to be in equilibrium. Can you identify the forces acting on each of these objects? For the signboard suspended to the ceiling, the signboard is held in place by the upward forces exerted by the cables. This contact force exerted by the cables on the signage is called tension. This force is drawn along the cable and points away from the object. Can you think of other objects that exert forces on the signboard? Intuitively, we know that something must be pulling down to balance the upward forces exerted on the signboard. This force must be the gravitational force. Earth pulls downward on the signboard toward the Earth's center. This non-contact force is equivalent to the weight of the object. For this signboard to stay in equilibrium, Newton's first law of motion implies that these forces must add up to zero. So, our equation would be 2t minus w is equal to 0. Then, we can say that t is equal to w over 2. This would mean that for the signage to stay in equilibrium, each cable must support half the weight of the signboard. What do you think will happen if the weight exceeds the tensile strength of the cables? You are right! The cables will break and the signage will fall to the ground. Now, consider the stack of books sitting on the table. How many objects are exerting forces on the books? Can you identify them? Excellent! 2 objects are exerting force on the book. The table exerts an upward force on the book. This contact force is drawn perpendicular to the table's surface. We call this force the normal force. The other forces is the gravitational force exerted by the Earth. If the total weight of the books is 20 Newton, the table must exert a force of 20 Newton on the books for the books to stay in equilibrium. Finally, let us consider the car resting on the ramp. How many contact forces and non-contact forces can you identify? Are the forces balanced? If you have identified 3, then you are correct. 3 forces are indeed acting on the car. 2 of the 3 forces are contact forces exerted by the ramp on the car. One of the forces is the normal force exerted by the ramp. The other force is the upward force along the ramp exerted on the car, which prevent it from sliding down the ramp. This force is called friction. The third force is the gravitational force directed downward perpendicular to the ground. Did you get the correct answers? If you did, congratulations! At a glance, the forces appear to be unbalanced. But careful inspection of the forces acting on the car shows that the vector sum of the friction force and normal force exerted on the car is equal in magnitude but opposite to the direction of the gravitational force. The forces are indeed balanced. The net force is zero and the object is in equilibrium. We are now ready to describe the magnitudes and directions of the forces acting on an object in equilibrium. Remember that the net force on an object in equilibrium is always equal to zero. Now, let's go to part 2, Quantitative Analysis. Let us consider the following examples. 3 ropes are tied to a very light ring. 2 of the ropes are attached to the wall at right angles. And the third rope is pulled with force of 250 Newton. If the ring is in equilibrium, what are the magnitudes and directions of the tensions in the first 2 ropes? Since the ring is in equilibrium, the net force acting on it must be zero. This would imply that the sum of all the forces acting on the ring along the horizontal and the sum of all the forces acting on the ring along the vertical must be zero. 3 forces are acting on the ring, namely the tension in the rope 1, tension in the rope 2, and the tension in the rope 3. The tension in the rope 3 can be resolved into its x and y component. We have T3x in horizontal to the right and T3y vertically downward. To solve for the tension in rope 3, we have T3x is equal to T3 times cosine 30 degrees. Then we substitute the given value, T3, 250 newtons, and cosine 30 degrees equal to 0.866. Then we multiply 250 newtons to 0.866. So the answer is positive 216.51 newtons. For the y component, we have T3y is equal to T3 times sine 30 degrees. Then we substitute the given value, T3 250 newtons, and sine 30 degrees equal to 0.5. Then we multiply 250 newtons to 0.5. So the answer is negative 125 newtons. So we can now solve for the tension in ropes 1 and 2. Since there is no motion along the vertical, the sum of all the forces along the vertical must be zero. Then we can say that T3y plus T1 equal to 0. T1 is equal to negative T3y. Then we substitute the value of T3y, which is negative 125 newtons. So our answer is positive 125 newtons. This means that the tension in rope 1 has a magnitude of 125 newtons directed upward. There is also no motion along the horizontal. Thus, the sum of all the forces acting on the ring along the horizontal must also be zero. So, the sum of all the forces are T3x plus T2 equal to 0. Then, we move T3x to the left side to get the value of T2. Then, we substitute the value of T3x, which is 216.51 newtons. So the final answer is negative 216.51 newtons. This means that the tension in rope 2 has a magnitude of 216.51 newtons and is directed to the left. Understanding Newton's first law of motion and the concept of equilibrium is essential in the design of industrial structures such as dams, buildings, and bridges, wherein the calculations of loads, tensile, and compressive stresses are necessary for the stability of these structures. A bridge, for example, is held up by the forces exerted by its supports, and the loads are the forces exerted by the weight of the object and the bridge itself. With all the bridges, there is only a certain weight or load that a bridge can support. Knowledge of Newton's first law of motion. In addition to studying the types of materials used, enables one to determine the maximum load that a particular bridge can hold before it buckles or before it snaps, as in the case of suspension bridge. So far, we have been analyzing forces acting on objects that are in a state of rest. How about those objects that are in motion, such as a car traveling on the highway or a skydiver plummeting towards the ground? Can the forces acting on them be balanced? That is, can the net force on them be equal to zero? When a skydiver jumps from a plane, the gravitational force on him causes him to accelerate downward, increasing his speed. But as he falls faster and faster, he encounters an increasing air drag until it equals the weight of the skydiver. At this point, the net force on the diver becomes zero. The diver no longer accelerates. The skydiver is said to have reached his terminal velocity. Opening his chute allows him to fall at that much lower terminal speed necessary for a safe landing. Isn't that amazing? Let us now check your understanding of Newton's first law of motion and the concept of equilibrium by answering the following questions. Congratulations, dear students! I hope you enjoy our today's episode. So that's all for today, guys. Don't forget and always remember, science not only amazing but fun! Bye-bye! See you on the next episode!